So this is lesson 6 on fitting linear models. So the first thing we need to do is go to lesson 6, and what you do is download the data file. This is an Excel file, so you'll actually need to download it from Google as an Excel file because Google will not open it. So you do that, and it'll be in your download folder, or you could put that in a special folder once you do that. And I already downloaded the R folder for lesson 6. So here's the R file. What I need to do though is import my lesson 6 data. So I go from Excel, browse, pick my download here. Then I'm going to import that. Now, one thing that I noticed is it calls it L6 data and then _1 underscore. So I'm going to actually have to change that a little bit and just call it L6 data. So I'm going to go L6 data and then assign that L6 data underscore the name of L6 data. So all that does is when I call some of my code, it'll be important to do that. So first, we've done that now. I'm going to go back here. We're going to talk about some of these associations. So, and I'm looking at this, we're going to identify the correlations as strong positive, positive, no correlations, negative, or strong negative. Now, all of the points seem to be very close to this line of best fit, and the line is going down, so this is strong negative. Here, this seems to be a strong positive. The line's going up. Most of the points are very close to it. So this is a strong positive correlation. Here again, most of the points are close to the line. It seems to be strong negative because the line is going down. Here, this appears to be no correlation. The line's kind of going up, but most of the points are way far away from it. So here, this seems to be a strong positive. The line's going up, the line of best fit, and most of the points are close to it. So now we're going to learn how to fit those with technology. So when we fit this is going to be the R code, but we're going to look at the output of the R code. So we're going to get our y-intercept and our line of best fit. We're also going to see is the intercept significant and is the x value significant? And then is the overall model significant? So here we get an F statistic and a P value to see if our model is significant. So what I'm going to do is show you how to run that in R. So first, I did the y variable is y1 if we look at our data. So I just did a bunch of like y1, we're going to say is approximately close to x1. So in order to do that, we go the y variable is L6 data money sign y1. So I run that. The x variable is L6 data money sign x1. And then our model is a linear model of y is, and then you put the tilde to x. And then to see the output, you go the summary of it. And now what I'm going to do is make this panel bigger so that you guys can see that a little bit better. So here is the intercept, or the value of the y-intercept, 5.11. Here is the value of the slope, 4.46 approximately. Here is if they're significant or not. So if this is below 0.05, it's significant. So the intercept is significant and the slope is very significant. And then you can look at the overall model. So the F statistic is 261.8. That's very large. And the p-value is 1.63 times 10 to the 09. How you'd express that is just saying the probability that this is significant is less than 0.001. So that model is very significant. So the line of best fit would be y is 5.11 plus 4.46x. You could switch that too and put y equals 4.46x plus 5.11. So what we're going to do is find the line of best fit for x2 and y2 and x3 and y3. So those are in here. We just fit our linear models. So I just called x and y, the y is the y2, x is the x2. And then I said model 2 is a linear model of y is approximately related to x. And then here is the summary of the model. So in looking at this, it would be y equals negative 5.11 minus 4.46x. Both terms are significant. The F statistic, again, is the same. And all that I did was just change the sign on the y values. That's why that happened. So what we can do is go to model 3, and we have y3 and x3. And then I just call those y and x, and I call this model 3 as a linear model of y is approximately equal to x. And then we just did a summary of the model. Now what you can do here is I can actually highlight all of those lines and click run, and it runs them all. So here our intercept is 7.07. Our slope is 3.61. Now, if you look, the intercept isn't exactly significant. It's probability is 0.07. Typically, that doesn't matter. You look at, is the x variable a predictor of y? And it is a significant predictor. The F statistic is 26.7, and the p-value is 0.0002, or you could say that's less than 0.001. So this is a significant predictor. And then remember too, you could look at different plots of these, but if I wanted to plot this, what you do is you want to actually plot x and then y. So if you did that, it would do a scatter plot of that. And then what you do is you could do the add line of that, of the linear model of y approximately related to x. And it would fit in your line of best fit. So just a couple things, because if you did a plot of model 3, that's actually going to show you some stuff we'll see in next lessons, but it'll do a plot of the residual values and some other things, not the actual scatter plot. So if I did a plot of that, it does multiple ones, and it does the residual values versus the fit. It does a normal probability plot, which you see all the lines are close to that. And it does a square root of the standardized residuals, and it does residuals versus the leverage plot. So it doesn't necessarily do what you would think it would do. So what we're going to do now is move on here. So we did y3, x3, and then we're going to do the same things and rewrite the code for x4, y4, and x5, y5, and do the line of best fit. So again, you can just run all three of these, and let me take out those things. So for the y4 and x4, we can just run all those lines of code. And then if you notice here, our line of best fit would be y equals negative 7.07 minus 3.61x. It looks to be both, well, the x is a significant predictor of y, and the F statistic is 26.7. The p-value is less than 0.05, so it's significant as well. And then here, if we did x5 and y5, we have the x-intercept, so y equals, the intercept is 23.69 plus 0.53x. Both are, if you look at the p-values, the intercept is significant, but really you want to look at the value for the x here, and it's not significant at all. So our F statistic is 0.13, and the probability is 0.71. And remember, that would have to be less than 0.05. And if you remember, if we wanted to look at, well, why is that not significant, we could do a plot of x and then y to make a scatter plot, and then look at that. Well, all of the points are very scattered. They're not close to, if I did a line of best fit, you do the ab line of the linear model of y is approximately equal to x. And you notice this ab line, oops, if I put that there, kind of, it goes through that, but a lot of the points are really far away from it. So now what we're going to do is look at, well, what is this correlation coefficient? How strong is a correlation? So we're going to find these correlation, and what you do is you look at the R value that's printed out. If R is between 0 and 0.25, it's no relationship. If it's negative, it's no relationship in the negative direction. This just tells you the line is going up. Here it's going down, but the slope is not significant. If it's between 0.25 and 0.5, it's a weak positive. Between negative 0.25 and negative 0.5, it's weak negative. Between 0.5 and 0.75, it's positive. Between negative 0.5 and negative 0.75, it's negative. And then above 0.75, but it would be less than 1. 1, it would be a perfect correlation, or like basically a deterministic function where its y is exactly x. And if it's less than negative 0.75, it's a strong negative. So what we're going to do is find the correlation coefficients. So here is how you do that. You omit the blank values, and then you just put core of xy. Method is Pearson. It's called the Pearson correlation coefficient, and that's actually called R. So this R Studio or R computer programming is named after his statistic. So here R for the first one is 0.97. That's strong positive. Here, if I wanted to do the correlation between x2 and y2, you can run those. And it's negative 0.97, so that's a strong negative correlation. And then if I want to run here for x3 and y3, running the appropriate code, it's 0.83, that's a strong positive. For x4 and y4, it is negative 0.83, which is a strong negative. And then here, for x5 and y5, it is, the correlation is 0.10, which is it's no correlation. And then to be able to draw a scatter plot, for example, we can look at here, let me go back. If I wanted to draw a scatter plot for the body mass index and the body fat percentage, and then try to fit a line of best fit, see what your slope is, what the equation might be. So you could do that by hand or just run that. So here is a scatter plot of this. This is health data. So as you see, as the body mass index increases, your body fat percentage goes up in general. And then we can do a linear model of this relationship where X is the BMI, Y is the body fat percentage. In looking at this, the equation would be Y equals negative 2.53 plus 1.42X, where X is your body mass index. And then in looking at that, X is a significant predictor. And then the F statistic is 261.7, and the p-value is 2.2 or less than 0.001. So you could use this equation to plug in someone's body mass index and then try to figure out, well, what would their body fat percentage be around? And then also we could find that correlation. How strong is the correlation between body mass index and body fat percentage? And it's 0.86, so it's a strong positive correlation. And then go ahead and do the check for understanding. And I would let students struggle through this. And this is very realistic health data as well.